Hey friends, so we got a lot going on here in lesson 3. There's kind of two things we want to talk about. The first thing we want to do is we want to review sigma notation, and that's going to take a little bit of time just to get you comfortable with what it looks like and what it means and what you do with it. And then we want to do an investigation that's going to lead us to a way that we can calculate the area underneath a curve, okay? Now, we alluded to that way back on day 1 in calculus, that if we made rectangles and we figured out the area of all those rectangles and we added them together, then that would be the area underneath the curve, okay? And so Riemann sum is one way to get there, okay? We are going to actually, over the course of the next few lessons, talk about a few different ways to get there. But Riemann sum is the first one that we're going to deal with, okay? Both of these topics are gonna maybe feel a little heavy at first. This might be a good video you watch once or twice, just to make sure you give yourself some processing time that you need, okay? So the first thing we want to do is we want to review sigma notation. We're going to use sigma notation towards the end of this lesson, so we need to just have kind of a mini lesson on what sigma notation is and what it means, okay? So we need to review sigma notation because the definite integral is the limit of a sum. More on that later, but notice I said the definite integral now instead of the indefinite integral, okay? Just as a spoiler alert, that's where we're going now. We're looking for definite integrals. Okay, anyway, this is the Greek letter sigma. Okay, and sigma refers in math to adding up a bunch of stuff, okay? And so the symbols that you're looking at would say the following, okay? This guy here, I just want to get my ink on, this guy here would be the thing that you're summing up, and then the bottom number here tells you where to start for your variable, and the top number tells you where to end. So essentially it means I would plug in 1 for I and get a number. I would plug in 2 for I and get a number. I would plug in 3 for I and get a number. I would plug in 4 for I and get a number. I would plug in 5 for I and get a number, and then I'd add all those numbers up. That's what this symbol tells you to do in a much more succinct way than what I just did, okay? Okay, so let's just clear that off the screen and we'll keep going here. So now in your book, they talk about certain ones that we're going to use, and there's 5 right at the top of your page there. There are 5 that I want you to understand what they are. So the sigma of 1, where I is 1 to n, will equal n, okay? And what we mean by that is no matter what I is, it's going to just be 1 because I'm not actually inputting in here. So I end up the first term's 1, the second term's 1, the third term's 1, the fourth term's 1. So I end up with 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Okay, so ultimately that's going to equal n because that's as far as I go. I go up to n. Okay. Okay. Well, what if I had a number other than 1 there? So what if I had some other sort of coefficient? So this is the summation of c from 1 to n. Well, that's going to equal c times whatever n is. Okay, so again, that's because the first term is going to be c, the second term is going to be c, the third term is going to be c, because it is only c, nothing's changing, right? So I go c plus c plus c plus c plus c all the way to the nth term of c. Well, that'll be n times c, okay? Okay. For I, we end up with this equation, n times n plus 1 all over 2, okay? So what we're saying is this would be the end result if this was the notation I was looking at, okay? If I is 1, then my first term's 1. My second term's 2 because I becomes 2. My third term's 3 because I becomes 3. My fourth term's 4 because I becomes 4. And I keep adding all those together all the way up to n. That all physically added together would equal this, n times n plus 1 all over 2. Okay, well, what if it was I squared? So I squared I just want to take my ink off and get my mouse back. Okay, I squared would be, your first term would be 1 squared, your second term would be 2 squared, your third term would be 3 squared, your fourth term would be 4 squared. And if I add them all together, it would actually become this formula. So again, what does this formula mean? Let's say n was 7, and I want to know what the total was. I just plug 7 into that formula. I don't need to go 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. I just plug 7 right into n here. So it'd be 7 times 8 times, what's that, 13, 15, and divided by 6, okay? Okay, what about if it was I cubed? Now, at this point of the game, you guys are staring at that top 5 things and you realize I cubed is my last one, and you're starting to stress out and freak out and you're saying, how am I supposed to remember all this? I would give you this if you needed it, okay? I'm not asking you to remember these 5 things, okay? Okay, so I cubed would end up being 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed all the way to n cubed. Well, how would I find out the summation of that? It would actually look like this, which would be n times n plus 1 all over 2 squared. Or we could simplify that to say n squared times n plus 1 all squared all over 4. I just squared each term. Okay. All right, so those are the first 5 that we're going to work with today. And now we just need to take some time to talk about exactly what we're doing with them. So the properties that you're going to see us do with summations are very similar to what you've seen us do with limits. Many things are comparable in what you can and can't do. So if I want to express these as monomial summations, the summation can actually be expressed on each term. But the first thing I need to do is I need to square 2 plus I. So 2 plus I all squared would be 4 plus 4I plus I squared. Okay, then this summation essentially can distribute to each term separately. So I'm looking at that. Okay, and so that would be the summation from 1 to n of 4 plus the summation of 1 to n of 4i, and then the coefficient can just come right to the front. It doesn't actually change the summation in the sense that whether I say it's 4 times that summation or whether I say it's the summation of 4i, it's going to be the same thing. So it's easier to put the coefficient in the front. Plus 4n, okay, because, so I also wrote this, I don't know if you caught that or not, but I changed the order. I wrote the highest degree to lowest degree. Okay, so I have the summation of I squared from this guy, plus 4 times the summation of I, plus 4n, because the summation of 4 would be 4n. Okay, again, I'm just taking that right off those first 5 that I showed you at the top of your page there. Okay. Okay, so now let's try this guy. We're going to go from 1 to 20, but again, I'm just expressing it as monomial summations. So this guy will be distributed to each one. So I end up with 3 times the summation of I squared minus 12 times the summation of I. Okay. I don't have to do anything with I right now because I haven't been asked to evaluate it. In a minute, I'm going to be asked to evaluate it. Okay. Again, this guy as monomial summation. So monomial again refers to one term, right? So I'm just taking the summation and distributing it through. So I would have 2 times the summation of I cubed minus 3 times the summation of I squared plus 5 times the summation of I minus 12n, because the summation of 12 is 12n. That was the second one that we did, okay, at the top of your page. Okay, so now you're being asked to evaluate. So I'm looking at the summation of 3i squared minus I, and I is going to be from 1 to n. Okay, so to evaluate this, the first thing I'm going to do is split it up into separate terms. So that's 3, the summation of I squared, minus the summation of I. Now I go to the top of the page. I know that the summation of I squared will become n times n plus 1 times 2n plus 1 all over 6. Okay, I have your book right here, and I'm just reading it off verbatim off the top. You're not have to memorize it. You just have to refer to it. Okay, so that becomes 3 times what I just said. And then I will be n times n plus 1 over 2 So I'm looking at this. So the first thing I'm going to do here is just say 3 over 6 is 1 over 2, and that actually gives me a common denominator. Okay. The next thing I'm going to do is I'm going to look at these terms and I'm going to say, hey, both of them involve an n, so I'll factor the n out, and both of them involve an n plus 1, so I'll factor the n plus 1 out. So I've got n times n plus 1 times, what would I be left with? I'd be left with 2n plus 1 minus 1. Just be careful that you realize that's subtraction there, okay? So n times n plus 1 times 2n plus 1 minus 1 all over 2. Okay, so now I can simplify this ever so slightly further. I've got 1 minus 1, which is nothing. So this is going to leave me with 2n. 2n times n would give me 2n squared, but then I can divide by 2 as well. So my simplified version is n squared times n plus 1. Now, what the heck did I just do? What does this mean? This refers to what the summation will equal depending on what n is. So if, say, I wanted to go from 1 to 5, I could plug 5 in here. That would be 25 times 6, okay? 25 times 6 is 150. So the summation of this equation from 1 to 5 would equal 150. That's what this says, okay? Okay, so for the next one, I'm looking at the summation of I being 1 to n of 2i cubed plus 3i minus 2. So again, I'm going to separate that out first. So that'll be 2 summation of I cubed plus 3 times summation of I minus 2n. Okay, now I know that the summation of I cubed equals n squared times n plus 1 squared over 4. I'm just reading that off your stuff at the top. And then the summation of I would be n times n plus 1 over 2. Okay, I need a common denominator. Well, first of all, this is 2 over 4, so that is 1 over 2, so that'll give me an over 2. Let's change that to 4n over 2 so that everything has a common denominator. Okay, so for this one, I'm actually going to, there's not a whole lot of common terms to take out. I could look at that and take out an n, but right now I'm just going to work on multiplying these out. So n plus 1 squared would give me n squared plus 2n plus 1. This would give me 3n squared plus 3n, and then that minus 4n. Okay. Now I can distribute the n squared. So n squared times n squared is n to the 4, n squared times 2n, and n squared times 1. Okay, now I'll combine like terms. So I've got n to the 4, and then I've got 2n cubed, I've got 4n squared, and then I've got minus n. Okay, now I want to see if I can factor that. I can take out an n from everything. So I'll have n over 2 times n cubed plus 2n squared plus 4n minus 1. Okay? Okay, so now we're going to actually get into our investigation on finding the area under a curve via something called Riemann sum. Okay, now, as a kind of disclaimer, it's very important that for the following questions, even if it's evident to you, which it's going to be for the first probably 2 of the 3 iterations that I do, the first 2, you're going to be like, I can do this in my head. Sure, but I'm trying to get you to map it out in a very specific way so that when I throw it all at you in example 3, that you're going to be able to stay with me. Okay, so you need to humor me as we go through this and watch very carefully how I write out my communication. Okay, the easy questions will help you figure out the difficult questions later on. So recall, way back on the first day of calculus, we found that to determine the area under a curve to the x-axis, we could use vertical rectangles where they all had equal base lengths. It worked great because then I can determine the rectangle area very easily, right? The area of rectangle is just length times width. And I could just add up all the rectangles and that would give me an idea of the area underneath the curve. Okay, so that's what we're going to do. You'll notice that you have 3 different diagrams here, part 1, part 2, part 3. Using graph 1, I'd like you to calculate the area between the curve and the x-axis from x equals 1 to x equals 5. So that means I want to go from x equals 1, so right here, to x equals 5. I'm going to be trying to figure out the area of that curve, okay? I want 4 vertical rectangles. Well, if I want 4 vertical rectangles, I'm going to place my vertical rectangles like so, okay? Now, what is the length base of each rectangle, and how did you determine this? Well, I can visually see right now the length is 1. But really what I did was I took the distance and I divided it by the amount of rectangles that I wanted to make, right? The total distance is 4. I went from 1 to 5. So the total distance is 4. I wanted 4 rectangles. 4 divided by 4. Each rectangle is going to have a base length of 1. Okay? So I went 5 minus 1 divided by 4. Okay? Estimate the height of each rectangle. Well, that I'm just going to take a look at here. The height's 1. I've got a height of what, 2.5. I got a height of 5, and I got a height of what, 8.5. Okay. Now I put there in brackets the last one, which is 13 as well, because that would be if I had been able to take this rectangle all the way up. That would have been my overestimation. Okay. You can imagine I could have made these rectangles. Actually, let me just draw you a picture of that for a sec. I could have actually made the rectangles look like this. And then I would have gotten new heights, right? But then I would have had an overestimation instead of an underestimation. You can see that this one's going to be an underestimation, right? Because of all this white space that's there. Okay. Okay. Using function notation, write the height of each rectangle you found in B. For instance, the height of the rectangle at x equals 3 would be f of 3. So essentially I want f of 1, f of 2, f of 3, f of 4, and so on. And so I have f of 1 is 1, f of 2 is 2.5, f of 3 is 5, f of 4 is 8.5, and then I also threw in there f of 5 being 13. Okay. All right, so calculate the total area. Well, how do I get the area? It's the base times the height. Okay, so it'd be the base times the height for rectangle 1, plus the base times the height for rectangle 2, plus the base times the height for rectangle 3, plus the base times the height for rectangle 4. But what I want you to notice there is the bases are all the same. So I could actually factor the base out. Okay, and so that would actually give me 1 times f of 1 plus f of 2 plus f of 3 plus f of 4. Okay, and I know that f of 1 was 1, f of 2 was 2.5, f of 3 was 5, and f of 4 was 8.5. So now I just add all that together and I get 17. Okay, so 17 units squared is my estimation for the area under the curve using 4 rectangles. Okay. All right, explain whether or not the area you found is an overestimate, an underestimate, or an exact calculation. Well, we just talked about that. It is definitely an underestimate because I've got white spots there that aren't included in my rectangle. Okay, so how do I make those white spots smaller? I make my rectangles skinnier. Okay, so in the second iteration of this, we're going to take a look at what if I made my base lengths to be a half instead of 1. So essentially, what if I did this? What if I cut this up into 8 rectangles instead of 4 rectangles? Okay. Okay, so now I want you to move to graph 2. Using graph number 2, calculate the area between the curve and the x-axis from x equals 1 to x equals 5. So same question, but now I want you to use 8 vertical rectangles and then answer the following questions. So if I was to do 8, that's what I'd be looking at. And I'm just going to hide my head for 1 second so that you can see where that ends up. Okay. Put myself back there. Okay. So now we're going to go through kind of the similar questions that we just did. What is the length of the base of each rectangle? Well, this time it's going to be a half. But how did I determine that? I took the distance, which was 5 minus 1, and I divided by the amount of rectangles that I wanted. So 5 minus 1 over 8, that equals 1/2. Okay. What is the approximate height of each rectangle? So I'm just going to go for rectangle 1, it's 1. For rectangle 2, it's about 1.5. For rectangle 3, it's about 2.5. Okay. So 1, 1.5, 2.5, 3.5, 5, 6.5, 8.5, 10.5. And then I still have in brackets that 13 because you could have done this with an overestimation instead of an underestimation. Okay. Okay, using function notation, write the height for each rectangle. So now we're looking at what's f of 1. F of 1 equals that height. F of 2 equals, actually it'll be f of 1.5 now. F of 2, f of 2.5, f of 3, and so on. Okay, so these should be all of the points you have. So for every one of these, I have a rectangle where I know the base length and I know the height. Okay, for my first rectangle, my base length is going to be a half, and the height is going to be whatever f of 1 was, which was 1. For the second one, my base length is going to be a half, and my height is going to be whatever f of 2 is, which is 2.5. So I essentially, if I want to add up all the areas of these rectangles, it's going to be 1/2 times f of 1 plus 1/2 times f of 2 plus 1/2 times f of 3 plus, and so on and so on and so on. But again, they all have 1/2. So I can actually factor the 1/2 to the front. Okay, so I factored the 1/2 to the front, and I've got f of 1 plus f of 1.5 plus f of 2. I plug in what all those values were, and then I just do the math. Okay, so that ends up with 19.5. So in my first estimation, I had 17 units squared. In my second estimation, I have 19.5 units squared. Okay, so now just a couple of conversations around that. So again, is this an overestimate, an underestimate, or an exact calculation? It is still an underestimate. I don't know why I'm struggling with that word. It's an underestimate. I want to say underestimation, I think, is my problem, but it's okay. It's all good. Forgive me. So it would be an underestimate as there is space still missing, okay? But it's less space than it was the first time. So this is actually a better estimation than it was the first time. So is the area you determined in part 2 better or worse than the area you determined in part 1? It's better. There's more rectangles, which means there's less space missing, okay? Just from those two investigations, you can imagine that really what we want to do is we want to make those rectangles so skinny that there's no missing space. And we can make those rectangles so skinny if we approach an infinite number of rectangles. And that's where we're now going to go with phase 3 or part 3 of our little investigation. Okay, so how could we determine more accurate estimates? The more rectangles we get, the bases become smaller and the more accurate we'll be. Okay, so enter part 3. Now, instead of going from 1 to 5, I'm going to ask you to go from A to B, and I'm going to ask you to have n vertical rectangles. Okay, but the questions I'm going to ask are very similar to the ones I just asked, and if you paid attention to how I set them up, you're going to feel okay with how I set this up. Okay, so what is the length of the base of each rectangle? Well, how would we do that? We figured out the distance and divided it by the amount of rectangles I wanted. So the distance here would be b minus a. Just like in the first example, it was 5 minus 1. Now it's b minus a over the number of rectangles that I want. This time the number of rectangles that I want is n. So b minus a over n equals that. Now that, you're used to saying delta x here because you are used to seeing that triangle as the change in. In this context, it actually refers to what we call the increment of x, okay? So the increment of x refers to how wide each increment of my rectangles are, okay? So when we're saying this guy, the increment of x is what we would say and the increment of x is b minus a over n. Okay, that is the representation of the length of the base for all of my rectangles. Okay. Now, using function notation, write the height of each rectangle. Well, remember what we did is we said, okay, when the base was a half, say, we started at f of 1. And so we said f of 1, then we went to f of 1.5, then we went to f of 2, then we went to f of 2.5. Okay, this time the base is the increment of x, right? We just said over here that the increment of x represents the length of the base of the rectangle. So we start with f of a. F of a is our first one, just like when we had numbers there, f of 1 was our first one, okay? But now, when it was a half, we went from 1 to 1.5, and the reason we did that was because the increment was a half, and so we just kept going up by halves. Well, now we don't know what the increment is, but we have a symbol for it. It's the increment of x. So we start at f of a, and then the next one will be f of a plus 1 increment. So we say f of a plus increment of x. The next one would be f of a plus 2 increments away. The next one would be f of a plus 3 increments away. And so you end up with this, f of a plus 1 increment, f of a plus 2 increments, f of a plus 3 increments, all the way to f of a plus 1 less than b. Okay, or 1 less than wherever we stop. In this case, it's b. I used n here to just represent wherever we would stop. Okay, and it's 1 less because we're always starting at the left of the rectangle, right? Not the right of the rectangle. Okay. So I just want to make sure you can visualize that because I don't want you at home scratching your head. If this is where I stop, right, this is actually my last rectangle. Do you know what I mean? And so this would be 1 increment away from the stop. That's why we have that n minus 1 there. Okay. Okay. So then, oops, sorry. So then, how do I get the total area? Well, all of the areas are base times height. So we got base times height plus the next base times height plus the next base times height plus the next base times height, right? Except that all the bases are the same, just like it was in the first example. All the bases were 1, so we factored out a 1. In the second example, all the bases were a half, so we factored out a half. In this example, all the bases are the increment of x. So we're going to factor out the increment of x, and we end up with the increment of x times f of a plus f of a plus 1 increment, f of a plus 2 increment, f of a plus 3 increment, and so on. Okay? All right. Now, think back to your work on series. What notation could we use to add up the infinite number of function terms? How could you incorporate this notation into your work with all of those heights? Hint, could you write all the heights as just one term? Okay, so sure, I can represent all my heights in just one term. That would involve a summation. I just add all those heights together, okay? So in order to add all those heights together, let me take you back to this guy for a second. Remember that the heights, this is what represented the heights, right? This represented the base, and this was the sum of all the heights. So we have f of a plus, the next one would be 1 increment away from that, so that height was represented as f of a plus 1 increment. Then the next height was represented as f of a plus 2 increments, and we added up all those heights. Okay, so let's say each one of those heights can be denoted as x subscript I. Okay, x subscript I. And let's say that x subscript I would be a plus whatever increment I'm on. Okay, so the very first one, I wasn't on an increment, so I would be 0, and that would leave me with just a. For the second one, that's the first increment, so I would be 1, and I'd be left with a plus first increment. Okay, and so on and so forth. And so what happens is I say, okay, x subscript I is a plus I increment of x. And now I say I want the summation of all of my heights. I want the summation of all of my x subscript i's, where I would go from 1 all the way up to n. Okay? I would go up from 1 all the way up to n. So that would represent all my heights put together. Okay? Now, the next question says, what about the limits? Not what about the limits? What about the rectangles? If I want to get as many rectangles as possible, essentially I want to look at that as a limit. Okay? And so I want to look at that as a limit of the increment of x. But remember that the increment of x was b minus a over n. So I'm going to look for the limit of b minus a over n as n approaches infinity. Okay, so now I have a representation of how to look at an infinite amount of bases for the triangle, and I have a representation of the summation of all the heights of my triangle. And essentially, I'm going to put those two things together, thinking that the area of a rectangle is base times height. Okay, so we're going to start tweaking the formula a little bit. So the area can be represented as the sum of all the areas of all the rectangles. Great. What we're really saying there is that it's the sum of all the heights times the base. Because remember, we could factor that base out, right? Because they all had the same base. So it's the base times the sum of all the heights. Okay. So if we look at that from a summation standpoint, we can say the sum of all the heights as I equals 1 to n times the base. Okay, so I want to mention here because earlier I had talked about the fact that, we started with a, when we were dealing with heights, we started with a, which was like 0. And then we went to a plus 1 increment, and then we went to a plus 2 increments, and all of those represented each of the varying heights as we went. And so we went actually from 0 to n minus 1. Now, summation equations don't work starting at 0. And so what we've done here to make it work with the summation formula, we've added 1 to both the bottom and the top. And so now instead of looking at it from I equals 0 to n minus 1, we're going to look at it from I equals 1 to n, okay? That way it matches the summation formula. So right now we're at, the area is the summation from I to n of the heights times the bases, okay? Now, that becomes the summation of all the heights, okay, times the bases, but we're trying to get an infinite amount of rectangles. So we're trying to get that number, that n, to be as large as possible so that the bases are as small as possible, right? And so what we do is we say, okay, well, those bases were b minus a over n, but now we want to look at that as the limit as n approaches infinity, okay? Well, we already know each of these things. We know that the heights are all now represented as f of x subscript I, and we know that all those bases are represented as the increment of x. And so we now have a formula for Riemann sum. The area will equal the limit as as n approaches infinity of the summation from 1 to n of f subscript I times the increment of x, where x subscript I is defined as a plus I increment of x, which we've already talked about in a previous slide. Okay, and again, these are formulas that you're given. Okay, you don't have to memorize all of these things, but what we've spent the last several minutes doing, for some of you probably feel like it's been several hours, what we spent time doing is trying to understand where this formula comes from, how it gets derived, okay? So now, in our last couple of examples together, I want to go through how it actually works, okay? We're actually gonna find the area underneath a curve and above the x-axis, and we're actually gonna do it two of them, one for a very, very straightforward one, and one for a slightly more complicated one. Okay, so the first one is our straightforward one. We're going to look at the area of the curve underneath the curve for f of x equals 3x plus 2 and above the x-axis on the interval from 1 to 3. Now we're going to do it two different ways. We're going to do it using the trapezoidal area formula, and then we're going to try it with a Riemann sum. Now, the trapezoidal area formula, when you see me do that, and then you see me do Riemann sum, you're going to be like, Hill, why the heck would we ever do Riemann sum when we can use the area of the trapezoid? I get it. The area of the trapezoid is going to be much easier, okay? But not everything is going to look like a trapezoid, and so you can't use the area of the trapezoid for everything. So I'm trying to show you with a simpler one that Riemann sum is going to give you the same area as using a simpler formula, because not everything's going to have a simple formula available to you. Okay, so trust me. Now, the area of a trapezoid ends up being the two bases added together divided by 2 times the height. Well, what are the two bases? Well, let me draw you a picture. If I look at this as a trapezoid, this is actually my two bases. My two bases are defined as the ones running parallel to each other. Okay, so this base is length 5 and this base is length 11. And then the height would have to be perpendicular to that. So the height would actually be 2 there. Okay, so I end up with, oh, sorry, I got to get my mouse back on. 5 plus 11 over 2 times 2, which is just 5 plus 11, so it's 16. The area of this trapezoid is 16 units squared. Okay, easy peasy, right? Now we're going to do the exact same question, but we're going to do it with Riemann sum. Okay, so for Riemann sum, we're looking at the summation of I, where I is 1 to n, of f of x subscript I times the increment of x. So we have to figure out what f of x subscript I have a very hard time saying that, and we have to figure out what the increment of x is. So we're going to start with the increment of x, because we know that the increment of x is b minus a over n, right? Well, b is 3 and a is 1. B is just where you stop and a is where you started. So I've got 3 minus 1 over n. Okay, so I need to establish what each of these guys are, and then I got a little ahead of my slide. So the increment of x is b minus a over n, and so that would be 2 over n. Okay. Okay, in order to figure out what f of x subscript I is, I need to figure out what x subscript I is first. And we have defined x subscript I as a plus I times the increment of x. Well, I already know that the increment of x is 2 over n. So I times the increment of x is just 2i over n. A is that starting point, which is, in this example, is 1. Okay, so x subscript I can be represented as 1 plus 2i over n. Great, but I don't want to know what x subscript I is. I want to know what f of x subscript I is. So for that, I have to hide my big old head and remind you that f of x is 3x plus 2. So if f of x is 3x plus 2, and I want f of x subscript I need to replace my x with x subscript I. So I need to replace my x with 1 plus 2i over n. Okay, so that's going to be 3 times x, but x is now 1 plus 2i over n, plus 2. Okay, all right, so now I'm going to clean that up a little bit. 3 times 1 is 3. I also have a plus 2 there, so that's going to add together to give me 5. And 3 times 2i over n would be 6i over n. So f of x subscript I is 5 plus 6i over n. Okay? All right, so now I know what the increment of x is, or how to represent it, and I know what f of x subscript I is. So I'm going to plug that into my Riemann sum. Okay, so I have, remember it was f of x subscript I, and that's 5 plus 6i over n. And then the increment of x was 2 over n. That's where those two things are coming from. Okay. All right. The 2 over n is just a coefficient. It has nothing to do with the summation, so that can come to the front. The summation will distribute to the 5 and to the 6i over n. So right now I'm looking at something like this guy. 2 over n times the summation of 5 plus the summation of 6i over n. Okay, the summation of 5 is 5n. Again, that's just coming from those first original 5 summation properties that I gave you at the beginning of this lesson. You know, that thing that felt like hours ago. And then for this guy, 6 over n has nothing to do with the summation, right? So I'll just put that in front. It'll be 6 over n times the summation of I. And the summation of I is another one that we were given. The summation of I is n times n plus 1 all over 2. So I've replaced the summation of I with n times n plus 1 all over 2. Now, my n's would divide each other out, and 6 over 2 is 3. So that's going to give me 5n plus 3 times n minus, or n plus 1. Okay. Now, 3n plus 3 when I distribute that, and so that'll be 8n plus 3. 2 over n times 8n would be 16, and 2 over n times 3 would give me 6 over n. So right now I've got the area is 16 plus 6 over n. Now, in order to figure out the actual area, I have to go back to thinking of this as a limit, and it's the limit as n approaches infinity, right? So as n approaches infinity, that 6 over n would become 0, and I'd be left with 16, which is exactly what I got when I did the trapezoid one. Okay, so 16 units squared. I've now shown it to you with a nice, simple, compact formula, and I've shown it to you with Riemann sum. Okay, again, if I was given the choice, I would just use the trapezoid formula, but not everything is going to be this pretty little trapezoid. Okay, and so Riemann sum will work regardless of the equation that I'm trying to find myself under. Okay. All right, so speaking of that, let's go slightly more complicated, and we want to look at the area under the curve from y equals x cubed, and I want to go from x equals 0 to x equals 4. So again, the area will be the summation from 1 to n of f of x subscript I and times the increment of x. So I have to figure out what, I have to go through that same process, right? I have to figure out what f of x subscript I is, and I have to figure out what the increment of x is. I'm going to start with the increment of x, that's b minus a over n. So that's 4 minus 0 over n, so that's 4 over n. Okay. I know that x subscript I is a plus I times the increment of x. Well, the increment of x is 4 over n, so I times the increment of x is 4i over n. And in this case, a was my starting value, which was 0. So that'd be 0 plus 4i over n, so it's just 4i over n. So x subscript I is denoted as 4i over n. So now I have to figure out what f of x subscript I is. So I take my f of x equation, which happens to be x cubed right here, and I replace my x with 4i over n. So I've got 4i over n cubed, which is 64i cubed over n cubed. Okay, so f of x subscript I is 64i cubed over n cubed. So now I'm ready to plug in back to my summation formula what f of x subscript I is and what the increment of x is. Okay, so I'm looking at f of x subscript I was 64i cubed over n cubed. And then the increment of x was 4 over n. Now, what just becomes coefficients to the front of this? Everything that doesn't involve I, essentially. So I've got 64 times 4, which would be 256, and n cubed times n, which would be n to the 4. So 256 over n to the 4 can come to the front, and I'm left with the summation of I cubed. Well, I know that the summation of I cubed is something that was given to me. It was one of those 5 original ones given to you like 18 hours ago. The summation of I cubed is n squared times n plus 1 squared all over 4. Okay? So I've replaced my summation of I cubed with n squared times n plus 1 squared all over 4. Now, before I get going here, let's clean a few things up if possible. I know that 256 divided by 4 will put me back to that 64. And I know that n squared over n to the 4 would give me n squared on the bottom. Okay, so that's going to give me just a little bit of a cleaner look here, 64 times n plus 1 squared all over n squared. Now I'll go and do the n plus 1 squared. So that'll be n squared plus 2n plus 1. Okay, and then I just moved my 64 to the front. Each one of these terms here is going to get divided by n squared. Okay, so n squared divided by n squared is 1, and 2n over n squared would give me 2 over n, and 1 over n squared. So I'm just splitting that up into 3 different terms. Okay. Some of you may feel like I'm ignoring the 64 divided by n squared, but I'm not really, because if this is 64 times that, it is still being divided by the n squared. Okay. Okay, but what I've really done here is I've set myself up so that I have a very nice limit conversation. That's why I wanted to set this up into those 3 different terms by dividing everything by n squared there. Okay, so now it looks like I'm ready to take the limit. So we end up with 64 times the limit as n approaches infinity of 1 plus 2 over n plus 1 over n squared. Well, as n approaches infinity, 2 over n will become 0. 1 over n squared will become 0. So I'm left with 64 times 1 plus 0, which is 64 times 1, which is 64. So the area under the curve will be 64 units squared. Okay. See, this is hours of fun. You guys can totally do this, okay? So your mission, should you choose to accept it, and you have to, is written here for you, okay? Take your time, make sure you're checking the answers, make sure you're communicating all these little itty bits and pieces. You know, tell me what each one is before you then go and plug it in so that you're communicating well. As always, if you have any questions, please connect with me. Okay, don't let questions go unasked. Okay, and I will see you for lesson 4 whenever you decide to play it. Okay, have a great time, and we'll catch you soon. Take care, guys.